record button. All right, if we take a look, 6 missed this out of the 19, that's okay. Pacemakers, electronic devices that help regulate the heart rate. Currently, lithium iodine cells are commonly used to power pacemakers and have replaced zinc mercury cells. Table 1 provides the operating cell potential for each. Table 2 provides the standard reduction potential for several half reactions related to zinc mercury cells. So if we take a look, both of these have positive. That's good, right? That means these cells are what? They're galvanic, they're spontaneous, they give off energy. The lithium iodine has what? Higher cell potential. So just if somebody just showed you the numbers and they were like, okay, this Corvette goes 160 miles per hour and this Mustang goes 120 miles per hour, if you were looking for speed, you would go with the Corvette, right? Let's take a look at the answers. During the initial cell operation, each reaction is thermodynamically favorable. So that's true. During each is thermodynamically favorable. So it's between A and B. Iodine, oxidation. Yeah, we don't even have the things for that. The mercury, gaining electrons, that's reduction. All right. So it's between A and B, but the larger operating potential of lithium iodine cell indicates that its cell reaction is more thermodynamically favorable. Yeah, I mean, right there, you see the 2.80. The larger operation is less, yeah. So no biggie there. Let's see why, I don't know why people pick that one. If we take a look, oxidation of mercury. Yeah, it doesn't make sense. Oxidation of iodine is not. We don't have either the reduction potential or that. Not sure why that one was picked either. But like I said, looking at these two numbers, boom, this one should stick out. Half and half here, basically. Same type of thing. Pacemakers are electronic devices that help regulate the heart rate. Same stuff. Table 1 provides cell potential. On average, after 1 year of operation, the potential of the lithium iodine cell decreases by 1 to 2%. Which of the following best explains that? So as we're looking at this reaction take place, we're no longer at the standard cell potential. If we take a look, products are going to increase over reactants. This is what makes a battery basically die out. I think the best way to do this would be to switch to this so you can see. If you recall, Q equals products over reactants. As the products increase, our Q changes. So if we look back at our formula for that, did they give the formula down here? Oh, here we go. It's the negative RT over NF, natural log of Q. So that becomes basically L cube, the natural log of Q becomes more positive over time. As this gets bigger, we are subtracting, more from it. So if our cell was at such and such a potential, if this is getting bigger, then we are subtracting more from it, and that's going to make the overall cell potential of the new one, as the battery goes on in life, lower. Q decreases. Well, we know that products on top, so that's not true. This would be just standard cell potential. So that would not be the case as time goes on, because you're not dealing with those ideals. And they love this one, don't they? The use of zinc mercury using the oxidation of zinc by O2 from air, generating potential of plus 1.60 volts. And reduction potentials. Which of the following explains the modification of the cell design that is most responsible for the difference in cell potential for zinc mercury slash and zinc airs? Let's mix here. So the greater standard cell potential of the zinc air compared to that of the zinc mercury cell most likely results from thermodynamically more favorable reduction of oxygen compared to boom versus boom, right? And that's basically all I put was high reduction potential. Let's see if the greater standard cell potential compared to that of zinc. So this is the most likely from the greater number of moles of electrons required. That's not, I mean, the reduction potential, that's not going to be a factor. The reduction potential is going to be a bigger thing. The greater standard cell potential of the zinc cell compared to that, most likely from the thermodynamically less favorable. Okay, and that's the opposite of the truth that we see here. Oxygen +4. So I could see this one, but you're not going to worry about that, the moles of electrons compared to this reduction potential. Diagram 1, diagram 2, diagram 3, diagram 4. We're looking for the one that identifies the physical processes, the correct delta S. So remember, delta S is spontaneity or entropy. If delta S is positive, that means it's gone to more disorder. So if we take a look here, diagram 1, this is freezing. From liquid to solid, more uniformly packed. So that would be negative right off the bat. Diagram 2, the process is melting. And that's the hard thing. If delta G is negative, that's favored. It's a spontaneous thing, but delta S is the one where you're looking for it to be positive to be more favorable for delta S. Delta H being negative, again, exothermic, that's more favored as you look at the reaction, but I think that may have been the problem with that one. 15-2, I think we've actually seen this problem many times already. Whenever you look at it, one of these has a larger distribution of energy, and that's this one. Sample 1, because the N2s have a larger distribution of energy. If you don't know how to read that, look at the actual arrows. The arrows are kind of a magnitude. I think most of you guys have taken physics, but that's shown with like force vectors and stuff like that, right? You draw the arrows longer with a bigger force or bigger. That's what they're doing here. Whereas we look at these, they're all very similar. I think that's good enough distribution. That's when we had some trouble with. Question 7. The chemical equation above represents the formation of selenium hexafluoride from its elements, and the table provides the approximate values of S. Based on the data, which of the following mathematical expressions can be used? So it's products minus reactants for delta S. So if we know delta S equals negative 337, we should be able to rearrange this equation mathematically. Let me show you how I did it. So if we take a look right here, I think I want to do this instead. This might be best. So I can go between the two. So if we take a look right here, we have 314. That is the product, SEF6. From that, just working well. From that, we're going to minus. We have how many F2s? We have 3. So we're going to minus the quantity here of 3 times whatever F2 is, which we don't know, plus the SE. So remember, it's the summation of the products minus the summation of the reactants. It's the same for all of those, like delta G, delta H. So that is basically a substitution problem. Looks like I rearranged this to get this, which is that what they got? Yep, 1/3, because it was 3x. So we had to take 1/3 from that whole thing. Boom, boom. Yeah. It's the summation of the products minus the summation of the reactants. So if you were given this F2, which we could calculate what it is, but I don't think it matters. You would add these together. You multiply this by 3, whatever the F2 is, and then you would add them. And then you would take the products and you would subtract the summation of those two. Oh, you are going to ask me the math for this. So let's see here. So we get 314 minus 3x plus 42, right? So you're saying, why isn't it negative sign here? You sure? By having this negative 1/3, that would become a negative. Okay. You smell smoke? No. Looking at this, that's exactly, yeah. That's what we have. The nine people, it was the problem with that negative. Oof, big one here. The table above provides the approximate S values for this based on which of the following reactants has the largest increase of entropy. To say the truth, I don't even know if you need to look at those. Do we? 2 moles of gas becoming 1 mole of gas. Is that an increase in entropy or not? No. 3 moles of gas going to 1 mole of gas. Is that an increase in entropy? No. 1 mole of gas going to 1 mole of gas. You lose a solid, so that may be. But here we have 1 mole of gas going to 2 moles of gas. You could do the math on that for sure all day long. But I mean, also just the idea of what entropy is, going to more disorder, that might be a quicker way to do it. What did I put? Yeah, delta S, yeah. Is definitely much greater than 0 on this guy. They actually calculated out for that. Yeah, they just gave you the actual calculations. A quick look shows that A is the largest blah. It seems like a common theme to have you be able to look at these without the numbers, especially something like, I mean, it wouldn't be hard to sit there and multiply through, get the products. But remember, on this section, you don't actually have a calculator. So, I mean, I would say that they're probably expecting you to be able to look at those and sit there and go, oh, a more disorder, 1 mole of gas to 2 moles of gas. 12 to 5. Time is getting the better of us right now. So I'm going to skip ahead because we're only on question 10. Ice cube melts when placed inside a room at 22 degrees Celsius based on the concepts of enthalpy, entropy, and Gibbs free energy. Which of the following explains why the process is thermodynamically favorable? What is the delta H? Is melting ice an endothermic or exothermic process? Endothermic. So delta H is going to be positive. Is that favorable? No, usually delta H, if we look at Gibbs free energy, right? It's the delta H minus, and the more negative Gibbs free energy is, the more spontaneous it is. So that's not favorable. So delta H is not less than 0. Delta H is not less than 0. Delta H is greater than 0. What happens to the particles whenever we melt? Are they more organized or less organized? Less organized. So right there, we know that delta S is greater than 0. So looking at that, we could sit there and do that with just this much, right? And then the rest is just explaining it. Half and half, 5 gram sample potassium hydroxide at 25 degrees Celsius added to 100 grams of hydrogen monoxide, room temperature, all the potassium hydroxide dissolved, the temperature of the solution has increased. Based on the following, what justifies a claim that the solution of potassium hydroxide is thermodynamically favorable? That's a lot. All right, so reading the first two, it says the forces between the ions and the water molecules. The energy required to separate the ions being less than the energy released is going to be favorable. What's that, the difference between that one and the top one? It's just that this one says is stronger than the forces between the water molecules. It's basically you have those particles being attracted to each other. The energy to pull them apart is less than the energy released. So that gives us delta H being less than 0. It's exothermic. See what I put here for question 11. And basically, I just put the formula there. So if we take a look, all of these things are good. We know this one is not good because this is not spontaneous and this is not spontaneous. So it's between these two. All of the delta H, delta S stuff is the same here. It's just the fact that the wording of this is not something that would be favorable. It's the fact that the energy to break the bonds between the ionic bonds between the compound is less than that is released. I'm trying to think. The answers on this are pretty spread out. Make sure that you know that these would not be a favorable process. So thermodynamically favorable process, you should be able to get rid of both of these immediately because delta G here it says is greater than 0. Oof. Fluorination of ammonium is represented by the balanced equation above. Approximate values of delta G for the reactants and products are given in the following table. Based on the information, which of the following statements best helps to explain whether or not the reaction is thermodynamically favorable? What do we want for delta G to be thermodynamically favorable? Less than 0. So right there, we know that B and D are not going to be possible answers. So delta G is less than 0 and the reaction is thermodynamic because the product molecules have more complex structures and greater absolute entropies than reactant molecules do. 3 moles, 1 mole, 3 moles, 1 mole. More complex structures. We could do the math on this. The summation of that does look like it would be higher. Delta G is less than 0 and the reaction is thermodynamic because the energy released when the bonds and the products are formed is greater. Yeah, it's going to be that formula again. The delta H minus delta S equals delta G for that. So yeah, They sit there and they show you that. Complex structures and greater absolute entropy. That sounds like, I don't even know, buzzwords. So it's going to be because the energy released that when the bonds in the products are formed is greater than the energy absorbed. So basically the energy required to break the bonds is less than the energy released whenever we are reforming these bonds. X undergoes two competing reactions represented above. The following graph shows the changes in energy. What do we know about a dotted line? Yeah, usually, but what's this X undergo? Oh, there's two different types of reactions. Yeah, reaction one, reaction two. In an experiment, yeah, I just read into it too much. An experiment done at low temperature 1 hour after the reaction started, Y was produced, but almost no Z was produced. Low temperature, Y was produced, but almost no Z was produced. At a much higher temperature, 1 hour after the reaction, both Y and Z had been produced. Which of the following explains why very little Z was produced at a lower temperature? Yeah, higher what? Higher activation energy. Yeah, there we go. Higher average kinetic energy of the molecules at a lower temperature resulted in very, nope. Average kinetic energy is right here. It says that it's at low temperature. This is not the average kinetic energy. This is the activation energy. So that's no good. A greater collision frequency between X molecules. If we're dealing with this low temperature, it's not going to be that. We're going to have, we should have the same type of collision. It's the fact that we have this higher activation energy to form the Z.
Can I ask a slightly off-topic question real quick?
No worries.
What percentage of the questions would you have to get right on the multiple choice to get like a passing score, like a 4 or a 3?
That's something I'd have to calculate. How many questions, like I can figure out, like I can find out how many questions and stuff like that are on there. It's not something I've actually considered, but I can look into it for you. Cool. Does it change every year? Yeah, so it's based on the average too. So I mean that would be something difficult. But I can look, I'm sure that somebody's figured out the math for that. Or yeah. If it's that important to you, I can look on there.
It's fine.
42%. So over 72, if you get 72%, you're a 5. Below that, 58 per 2 below the 71 to 58 would be a 4. And that's a 3. That's low. Right? There you go. Thank you. Graphite. Graphite's an ultracarbon. Oof, we are so slow on time. If we look at these, which of these is more organized? Synthetic diamonds have carbons in a hexagonal versus diamonds with in the cubic lattice are not produced, even though they are thermodynamically more stable. What does it take to make a diamond? It takes pressure and heat and time and carbon. I like that, Don. Yes, it definitely takes carbon. So what we're dealing here with is another activation energy thing. The activation energy needed to form cubic diamond is much greater than that to form the hexagonal. Just like the thing we were dealing with here, being at a low temperature, we just don't have the energy, the activation energy required to form that. So however these diamonds take billions of years or longer, basically they just don't have the activation energy. They just can't get over that hump. And the amount of energy required to create new bonds between carbon atoms and carbon is much greater. New bonds between carbon and cubic is much smaller. You guys got confused on the thing there, yeah. It's just like, I mean, if you just take this question and you sit here and you see this, it's going to be an activation energy thing. Skip. Oof. The 720 degrees Celsius, the reaction represented above has an equilibrium constant of that, which is the following mathematical expressions can be used to support the claim. So again, if we take a look, both of these, no good because delta G is less than 0, so that would be thermodynamically favored. We want to show that it's not thermodynamically favored. We take a look here. Here's the K. If we look at the formula, negative RT, natural log of K, negative RT. There's the change from Celsius to Kelvin, so that's T, natural log of K. And there we go. Boom. I need to get, where did you get that printout of the newest one? Was it from the AP website? I need to make sure I get you guys a copy of that. The new formula sheet.
Oh,
Is this something Mr. Barugi gave you guys last semester? Okay. So you guys should all have that then from him. Cool. Let's do this one. The chemical equation and thermodynamic data for the melting of tungsten are given above. Based on this information, which is the following, provides the press prediction, which correction justification about whether a sample of pure tungsten will melt. When you're dealing with that, you have the idea that basically the melting point is K equaling 0. So at the melting point, the solid and liquid phase are equilibrium. Yeah, there we go. So the delta G is equal to 0 there. So wherever that Tm, the melting temperature is, it's basically just the formula. So let's take a look at these answers because they're not actually, they're putting it in the formula, but they're not necessarily going for it. So delta H of fusion, the T is greater than the delta H of fusion divided by the delta S of fusion. Yeah, if you just rearrange this formula, you should be able to see that. Boom. So what would we do? We would add T delta S to both sides. And then we would divide both sides by delta S. So that puts delta S on the bottom of the delta H. Does that make sense? Because it has to be equal to 0 because you are at equilibrium for that. So delta G would be at equal to 0. What we got here, 12, geez. The chemical equations above, that's gonna do it for us, guys. I'm actually not gonna be here tomorrow, so